So we're going to continue with the presentations. And we have three lined up: autonomous driving, ML for healthcare, and computer vision. So let's start with autonomous driving. And this group is Kartik Agarwal, Urjest Beshaj, and Abhinav Gupta, who will be making the presentation.
I'll be sharing the screen, and we all will be speaking through my computer itself.
All right, that's good. So I'll make you co-host here. Okay, and I want to just mention that we do need to stop pretty much at 2:45. So I would appreciate your staying within the 30-minute limit, please.
We'll try our best, Professor.
Go ahead.
Right. Can you see our screen?
Yes.
Okay.
Awesome. So we are taking a deep dive into machine learning for autonomous vehicles for our final project. And just a brief summary of what we intend to cover. We're going to cover some of the taxonomy, some of the evaluation metrics, do some deep dives and head-to-head comparisons of different algorithms and data sets, and then talk about some more application-specific implementation using YOLO v7, and then talk about some open challenges and some ethics at the end. So just, very quickly, we all are pretty familiar with what an autonomous vehicle is. There's level 0 to level 5 of autonomy. We're at around level 2, 3 at the moment. And an autonomous vehicle is pretty much just a box with a bunch of sensors on wheels from our perspective. Sensors like LiDAR, RGB cameras, distance sensors, and so on and so forth. And so how we process this data and how we make sense of it from a controls perspective is what this project is all about. And therefore, the applications of machine learning in this space are tremendous. There's lots of perceptions and sensor fusion problems. These are the two that we'll be focusing on in our presentation. And specifically within perception, we'll be talking about object detection and lane detection, both part of computer vision.
So for scene understanding, which encapsulates object detection and lane detection, we'll have this delineation because we'd want to separate the high-level and low-level functionality of an autonomous vehicle. For instance, in lane detection, we typically want some high-level functionality of staying in the lane when the car is detecting the road, as compared to some more low-level functionalities, as compared as in some behavior in terms of path planning when the car stops, when the car is supposed to accelerate, specific maneuvers when an object is in sight, maybe a right light is red or green. In that case, object detectors, we'll have different types, and we'll be focusing more on YOLO and faster RCNN. We have a lot of data available in all of these cases. For lane detection,
for lane detection, we're going to be looking at something called stage CNN and using the CU lane dataset. And we'll explain why we've made this decision when we get there.
So regarding the sensor fusion techniques, we have both classical and deep learning based approaches. But why we need deep learning approaches when we already have classical techniques that are robust and have shown their power? So we are interested in deep learning because it can inherently handle high-dimensional data from multiple sensors and learn complex patterns. The deep learning approaches can be split into convolutional neural network and recurrent neural network. Within CNNs, we have both two-stage and single-stage methods, where the two-stage methods include RCNN, involved an initial step of proposing regions and the second step of detecting the objects. For the single-stage methods like YOLO, they perform region proposal and object detection in a single step, leading to a faster processing times, but sometimes at the cost of reduced performance. On the other side, for RNNs, we have long short-term memory and gated recurrent unit, both designed to handle sequence prediction tasks and making them particularly effective for time series data.
And then we'll briefly touch on some evaluation metrics. And so the primary way to evaluate an algorithm is the mean average precision, the MAP. We're familiar with this from class. And this has some specific instances. So the confusion matrix, the intersection over union, the recall, and the precision. So on the left, we have intersection over union, which is very simply just looking at the overlap between what you guess and what is the truth. of the bounding box. And then in the middle, we have the confusion matrix. Recall is just the number of correct predictions against the ground truth, and precision indicates the prediction accuracy. And on the rightmost, we can see a sample PR curve and a sample F1 curve. So increasing the area under the curve for the sample PR curve, we would indicate higher precision.
Right. So as Ergis mentioned, we have single stage and multi-stage detectors, and this is applicable for object detection as well. As he mentioned, the main difference is the region proposal network in the two-stage detectors. Both in the single state detector, the whole detection is made in a single network without the need for the region proposal network. And they contain a single feed-forward, fully convolutional network that directly provides the bounding boxes and object classification all in the same area. Extreme foreground background imbalance in the images, prevents these one-stage models from, achieving high accuracy, and they have a hard time, detecting objects with a good confidence, which are very small in the frame itself. On the left, we have three different approaches to how we can view these networks. We have a backbone, which is typically made of a convolutional neural network, could be a VGG or a ResNet popularly. And then we have bounding boxes and confidence thresholds, which are outputted from these single stage detectors. YOLO is a very popular example, and YOLO V7 specifically. And we have the architecture on the bottom left, which is fairly consistent with what the general architecture for single shot detectors is. What YOLO does is that it separates the whole image into a S by S grid, and then generates proposals, multiple proposals for the same object inside the image, and based on some non-maximum suppression and confidence thresholds, it generates bounding boxes and assigns a category to all of them. In contrast, two-stage frameworks divide the detection process into region proposal and the classification stage, which is just an addition on top of the single-stage detectors. These models propose several object candidates known as regions of interests, and then use reference boxes, anchors to generate the classification. And in the second step, the proposals are classified and the localization is defined. We have faster RCNN, which is a very popular example again of two-stage detectors, in which we have an input image with fully convolutional networks, which generates a feature map, proposes the regions. We do some ROI pooling to sparsify the whole proposal regions, and then categorize, classify, and then provide bounding boxes for all of these.
So Kartiki mentioned that we use many sensors in an AV, but why we need that? We need that because the sensor's performance is degraded in various ways and over time. So we are interested in using multiple of them and fuse their readings at various levels. This approach seeks to compensate for the limitation of individual sensors and yield an output that is robust, reliable, and accurate. The sensor fusion, we can divide it into three categories: data fusion, feature fusion, and decision fusion. The data fusion is the early combination of the raw sensor data. It offers more complete data, but it's computationally heavy and struggles with conflicting sensor data. Regarding the decision fusion or late fusion, it processes independently and extracts independently each sensor and fuse the results at the decision level. It manages conflicting data better and is less computing intensive, but may lose crucial data correlation. And regarding the third approach, feature fusion, it merges aspects of early and late fusion, and it fuses sensor data at different stages based on the situation. For example, it can fuse some data early to reduce noise, while other data can be fused later to retain independent decision making. This algorithm aims to improve the performance through optimizing data correlation and computational efficiency. Here we discuss the architecture of LSTMs that is part of the RNN structure. LSTMs use memory cells to store and update information over time. These cells have three gates: the input, the output, and the forget gate. We can think about those like a conveyor belt, where the cell carries the important information and the gate decides if we want to keep it or discard it. The gates use the sigmoid function to do that. This process aims to mitigate short-term memory issues that are related to the RNN structures. LSTMs use these 4 steps. The first one is the forget gate. It determines information to retain or discard. This gate uses the previous hidden state and the current input through the sigmoid function that generates values between 0 and 1. The second stage is the input gate, where it updates the cell state. It passes the previous hidden state and the current input through both a sigmoid function and a hyperbolic tangent function. The result from the hyperbolic tangent is then multiplied with the sigmoid output to decide the important information that we want to keep. The third stage is the cell state calculation. It is achieved by pointwise multiplying the cell state by the forget vector. And then we add the result from the input gate. This updates the cell state with relevant values identified by the networks. And finally, we have the output gate that decides the next hidden state. It passes the previous hidden state and current input through a sigmoid function, and then modified cell state through hyperbolic tangent. The output from both is then multiplied to determine the information the hidden state should carry. Here we have an application of this algorithm. We show a framework for 3D object detection using LiDAR data and an LSTM-based sequential point cloud processing approach. The idea is simple yet powerful. For each frame, we take point cloud features and merge them with memory and hidden features from the prior frame. This combined information allows us to predict 3D objects in the current frame. We can see this in the middle layer, the red dots. Above we have the data, and below that we have the time. We just fuse them and get the results that are shown.
Next, we talk about some methodology assessment between the two algorithms we mentioned, in this case, YOLO V7 and faster RCNN, in the context of object detection. So on the left side, we have some high-level comparisons. So we have the inference rates for the YOLO V7 E6 model, which is the base model for YOLO V7, and RCNN R101, which uses a ResNet 101 backbone. The inference rates are clearly skewed towards the YOLO V7, which has a faster inference rate, but potentially lower accuracy, as we'll see next. The complexity is a single stage versus a two-stage architecture. And the key features which are advertised or mentioned in the literature is that YOLO V7 uses a bag of freebies to improve the detection speed while maintaining the accuracy, while RCNNs use anchors, a set number of anchors to generate the regions of interest. We have low latency data sample requirements and hardware requirements for YOLO V7 as compared to RCNN. And the trainable parameter count is also significantly low, which means that YOLO V7 can be deployed on lighter hardware as compared to faster RCNNs. The input aspect ratios is typically 1:1 for both of these networks, and the applications depend on what you want. It could potentially be high accuracy or maybe real-time object detection. So you want to use YOLO V7 in areas where you want speed. So autonomous driving is the one. The second table shows some standardized metrics. So on standard data sets, so we have COCO 2017 and Pascal VOC 07. We have faster RCNN, published in 2015, and achieves a very high accuracy, the mean average precision on a V100 GPU, with the gigaflops, the floating operations per second, with an inference rate of 30 frames, going as low as 5. YOLO V7 gives very high frame rates with lesser number of floating point operations, but the mean average precision is generally low in these data sets. We could not find literature mentioning Pascal VOC for YOLO V7, so we had to skip that. Next.
Next, we'll be talking a bit about the lane marker detection aspect. So fundamentally, it's a very low level first order problem, right? Where are the lane markings, and where is the car relative to the lane markings? It's a very simple problem on the surface, but it becomes extremely complicated in the real world with environmental factors, right? So those would include things like markings being unclear, rubbed away, in poor shape, snow, etc. If the world was ideal, you could use something like canny edge detection, which is a wildly simplistic approach, which pretty much just extracts the edges from any image, and it leaves a grayscale binary, which makes computation very inexpensive and fast. It actually does this by applying a Gaussian to convert the grayscale and filter out the noise, which softens the image. And then it applies an intensity gradient by calculating the first and second derivatives, and then a few other steps. And then at the end, in hysteresis, it actually takes 8 points to check weak edges, because it determines if there are weak edges and strong edges. So it checks the weak edges to see if there are true edges by finding relationships to strong edges. Again, good and clean in ideal conditions, but would really struggle in noisy conditions, as you can see on the right, where it's nice and clean and it looks great. So this really highlights the need for a machine learning focused approach to this problem. The data set that we've chosen for this problem is the CU lane data set, which is a somewhat new data set. And it is regarded as one of the most challenging and most all-encompassing data sets. And it was trained on the streets of Beijing, very traffic-dense city. So it's also a very well-written and published about data set, as you can see, with over time the trends being, there's lots of papers coming out about this data set. So next slide. The algorithm that we are going to be talking about from literature is the spatial CNN algorithm, or the SCNN. And this actually comes from the developers of the CU lane dataset. Now, convolutional neural networks, CNNs, are usually built by stacking convolutional operations layer by layer. So as you can see in the first stack on the left image. And they're really good at extracting patterns from raw pixels. But what is important for lane detection is exploring the spatial relationships, since it's a moving vehicle. And there's large elongated objects such as poles, trucks, things like that. And there can be incomplete or distorted input data. As you can see, the CNN really struggles with this, whereas the SCNN, which takes the scene into account, doesn't. The way it does that is by viewing rows and columns of feature maps as layers, and then applies the convolution, nonlinear activation, and some operation sequentially, forming a deep neural network. Finally, it also has a computational advantage over traditional CNNs, since you're not comparing each pixel against each other pixel directly. Rather, there's a sequential passing scheme that takes a lot of redundancy out from the CNN approach. In fact, this SCNN approach, when it came out, was 8.7% faster, or sorry, more accurate than an RNN-based approach, and 4.6% faster than the CNN-based approach at the time. So it's extremely beneficial for elongated objects such as trucks, poles, and barriers, and there's much more spatial awareness. And we can see its accuracy compared against the other algorithms here. So the CU lane dataset consists of 8 special case scenarios, so normal plus 8 others. And in all of those, we can see that SCNN is generally the most accurate one. And you can see it in the images as well, where the SCNN is able to draw a complete lane, where there is not really for a lot of the other algorithms, or certainly not as consistent.
So among the algorithms that we previously mentioned for sensor fusion, the LSTM and faster RCNN are those two that are mostly used. It's very hard to compare those two algorithms because they are not the same. And it's like not comparing apples to apples. Looking at the type of data they handle, LSTMs excel at processing time series data, the kind we typically get from sensors like radar, LiDAR, and IMUs. On the other hand, faster RCNN is a model designed to process spatial data. It's particularly effective with images, which we often capture from cameras. Now, in terms of their primary uses, LSTMs are typically employed for sequence prediction tasks. For instance, they are great at predicting future positions of objects or helping in path planning for the vehicle. Faster RCNN is used for object detection tasks. It's capable of identifying multiple objects within images, such as cars, pedestrians, or traffic signs. When we talk about processing speed, both models have their strengths and weaknesses. LSTMs can be quite efficient for smaller data sets or short sequences, but when the sequences are long, their sequential processing nature can make them slow. Faster RCNN is efficient in processing complex image data, thanks to its ability to handle the entire image in one forward pass. However, its speed can vary based on the complexity of the image and the number of objects to detect. Regarding complexity, faster RCNN has a higher model complexity due to its multiple components like convolutional neural network and regional proposal networks, whereas LSTMs is somewhat simpler as it primarily deals with temporal dependencies in data. We can mention that both models require extensive training. LSTMs are trained on time series data and are sensitive to the sequence length and order, whereas faster RCNN is trained on image data with object annotations with no sensitivity to sequence order. In terms of the hardware requirements, LSTMs can be trained on common hardware setups, although GPUs can speed up the process. Whereas for faster RCNN, because of its model complexity, we generally require a high-end GPU. And finally, on their robustness, LSTMs are capable of capturing long-term temporal dependencies, although they can suffer from problems like exploding gradients. For faster RCNN, they are excellent at currently detaching multiple objects in a scene, but it can be sensitive to variations in object size or orientation.
Right. So now we come to an application-specific implementation. So we talked about object detection and we talked about YOLO V7, but here we talk about using YOLO V7 in a very specific condition, which is using hyperspectral imagery for obstacle detection in autonomous driving applications. And the dataset we're using is the Teledyne FLIR dataset, which consists of many classes, out of which we've highlighted the five most significant ones. And on the bottom left, we have the thermal image and the corresponding RG frames. The imaging setup consists of a thermal and visible camera, and both of those are mounted on a vehicle. The FOVs and the placements are slightly different, which is why you'll notice that on the bottom left, the corresponding frames have some displacement or some discrepancies, even though they correspond to the same time frame. We directly jump into the results. So you typically have a COCO trained YOLO V7 model, which we applied to the data set and just thermal images and see if we are able to extract any information based on the shape itself. And as expected, the performance was very poor, except for detecting people and cars, because probably the data points were very high in number. We are using evaluation metrics of precision recall at the max F1 score, average precision at 0.5 IOU, and average precision at an IOU range of 0.5 to 0.95 in increments of 0.05. Based on that, we take out the confusion matrix and see that most of the correct predictions are made for persons and cars, and we focus on that next. We completely retrain the thermal, the network on thermal images from scratch, and these are the precision recall and the F1 confidence scores, the curves available. Based on that, we compare the thermal versus RGB model performance. We have a baseline highlighted in the Teledyne FLIR dataset, which is the YOLO XM network, and we have its performance on FLIR dataset, the FLIR images for a person, FLIR images for a car, and same for RGB images for persons and cars, respectively. For YOLO V7, we also have the COCO dataset evaluation on a person, and we have the Teledyne FLIR dataset. And we see that if the YOLO V7 network, which is trained on the COCO dataset only, performs very poorly, as I highlighted in the last slide, and it offers a very low map score of 0.531. As soon as you train it on thermal images, as expected, the map score goes up for thermal images, but it remains fairly constant for RGB images, as is expected. The training parameters are set to 50 epochs with a batch size of 32. The confidence threshold is set to 0.25, and a training validation split is of 80-20 in this case. Based on that, we do some further experimentation on the YOLO V7 network for thermal images specifically. We retrain the full model with different batch sizes of 16 and 32. We freeze the backbone, which is the ELAN network in this case. And we also freeze the first 73 layers, which is up to the auxiliary head of the network, and see how well the network performs or how much the performance degrades. So as expected, the full model retraining actually improves the performance for person and car, as is expected, but the batch size doesn't really affect the whole thing. Freezing the backbone hampers some performance, but it is comparable if you freeze till only the backbone or freeze it till the auxiliary head. So these are some of the results which we obtained. Next, we have some fully trained RGB versus FLIR model comparisons as a demo. So as you can see on the first 3 images in the top row, those correspond to the RGB frames, and the bottom 3 images correspond to the same time frame in the IR camera, what the IR camera sees. So on the left side, we have a person walking across the street, which is completely not visible in the RGB frame. So which is why using thermal imagery is recommended in certain cases. Now, the challenge is that thermal imagery can help with occlusion, so which is the case in the first and the third images, in which we have RGB scenes in rainy conditions, in which the cars, incoming cars are not detected by the network, but thermal camera can easily detect those. During daytime, the opposite happens, that due to air pollution through sunlight, if you're not using the appropriate sensors, there's some air noise, which causes false detections or maybe missing detections altogether. So which is why we thought, why not merge the two? So we propose something which is based on the ambient light available in the environment. So typically in autonomous driving scenes, we have the top half of the frame, which indicates if it is day or if it is night. So we use that as a basis to merge those two. So we have an RGB frame which detects nothing. We have an IR camera which detects something, and we use the IR information, the inference from the IR network, to overlay those onto the RGB network's inference, which may or may not be present. So this requires some calibration, because we mentioned earlier that the FOVs of both the cameras and the placements are different. So there's some skewness involved. So which is why this is somewhat error prone if proper calibration is not done. So that is one of the things that we did. Next, we move to ethics and some challenges.
Yeah. So it wouldn't be a well-rounded discussion about autonomous vehicles if we didn't at least briefly touch on ethics. And since we are at the autonomous level 3, 2, 3 at the moment, what's keeping us from going to 5? And one of the big discussions is ethics. How should an autonomous vehicle act? Who does it prioritize, and why? And who's responsible for accidents? Is it the car? Is it the person driving the car? Is there a good answer here? And a lot of this comes from the trolley problem, which is pretty much, would you pull a lever to kill 5 people or 1 person? And there's plenty of derivatives of the trolley problem, as you can see from this image of the MIT moral machine, which explores this in great detail. And does it even matter? If the overall incident rate is compared to humans is lower, perhaps we declare victory and don't care about it. Perhaps all of these questions are impossible to answer, but one perspective comes from the Stanford Human-Centered Artificial Intelligence Lab, which is based on the duty of care and social contract principle. Fundamentally, and I'm greatly simplifying their solution here, their suggestion is to reject the concept of the trolley problem, which this is being turned into, and say that, oh, it's about social contract. If your self-driving car is perfect and someone swerves into it, it must do everything in its power to minimize damage. But if it must damage something or hurt someone, it is the person who broke the law. One potential flaw in their reasoning is that they assume that the self-driving vehicle is always perfect. What if it itself is making a mistake? Then what? Perfection is hard to discuss. But these questions, we don't aim to answer them. We just aim to bring them for a well-rounded presentation. And finally, just briefly touching on some other challenges to reaching level 5 or 4 autonomous driving. There's a significant cost improvement ratio problem. Every time you want to do more with the car, you would have to invest in better GPUs and computation, which will be expensive to do. And so is the cost worth it? There's also sensor limitations. No sensor is 100% accurate. So level 5 requires a certain level of redundancy that we just don't have yet. And interference latency, again, relates back to adding more computation power. And so does compute requirements. And then finally, commercial realizability. Can this be done at scale, practically? A lot of self-driving requires cars talking to each other. And so is that going to be able to happen at scale? Those are some of the hurdles in the way of autonomous vehicles. And that wraps up our presentation.
Thank you very much. All right, very good. So let me ask, I think with respect to, well, first of all, one important question maybe is, which company has the best autonomous driving system right now? You guys know?
So Waymo, that is in England, they are above Tesla in that.
They're what?
They are above Tesla in their autonomous driving system.
Okay. And who's using Waymo?
It is, I believe, under Uber. It's or Google. Google, under Google. Google is inventing the technology,
Right,
but
right.
yeah, it's not commercial yet.
It's not commercial yet, yeah. But among the commercial players, I guess they're all pretty low level, right?
Yeah, around level, the maximum is level 3, I believe.
I think Zoox is actually commercializing the AV space in terms of taxis, robo taxis. So they have actually rolled out fully self-driving robo taxis in California, I believe. That's I think hosted by Amazon. So
Which
they're
company?
still
What is it called?
Zoox, ZOOX.
Okay, yeah. I mean, I haven't used them, so I guess it's just coming out, right?
No, I think it has been in development, but they have
Okay.
rolled out the commercial aspects recently in the last 2-3 years.
Okay, very good. I think I'll just make a comment about the ethics of the thing. I mean, I don't think that I think the question for engineers really is to how do you realize a particular kind of social value, or because I mean you can or argue all day about this. I think that the question is, can you build a system that actually can realize any of those social value systems that social philosophers want to adopt, right? I mean, the question is, I mean, whether you would choose one versus the other, that's a really philosophical question. But I think engineers, right? I mean, I don't know if people have that attitude or not, but it seems to me that that's the attitude they should, if you choose a particular kind of choose a particular way of solving the train question, then you have to be able to implement it, right?
Yeah, completely agree, Professor. And
Yeah, I mean, yeah.
the Stanford HAI lab was taking a similar approach where they're sort of taking the part of it is taking an engineering centered approach, because at some point you have to move forward with technology and the debate on philosophicalness.
Yeah. Because I think the problem is I have a big problem with people who are engineers trying to make decisions about philosophy, and I equally have a problem with philosophers trying to solve problems in engineering, right? So you want to stick to what you're good at, and you have some sort of some sort of interface between the two, right? You want to say, if I input a particular ethics system into my system, then I should be able to realize it. All right, that's my comment there. I think we better move on to the next presentation. If anybody has any other questions on this one. Okay, so moving on. Thank you very much.
Thank you.
And next presentation will be machine learning for healthcare. Vlad Cernan, I think you guys all did a pretty good job. And we learned a lot. That was the whole point of this, is to learn as much as we can about how machine learning is being applied in various areas. And well, I hope you had the experience when you're going through the project to see that everything we learned in class is really applicable and really useful for all of these applications, right? They pop up all over the place. And I think that at this point, enough from the class to be able to launch yourself into these fields. So I think I'm very, glad that this is worked out. And the topics are very interesting. So if you haven't yet sent me the slides for the projects, please do so. We're gonna upload all of these things onto the Canvas site so everybody can access them, and then use them for your own projects, or if you just want to know more about the field. So I think it'll be really useful. Okay, and then we also need the reports. So as I said, the reports are due tomorrow. So if you could send them by the end of tomorrow would be really good, because we will need time to read them. And we'll need a couple of days to read them, right? And so please upload them on Canvas, just as you would upload a homework at the end of tomorrow. Okay. Then the other thing is that, please go and fill out the trace evaluations for the class. It's really important to get feedback on the class. And specifically, because this class is still evolving in some sense, so we need some feedback, and really looking forward to your comments. So if after you fill out the trace evaluations, please send me the receipt of the trace evaluations, because I'll just give some incentive. I might, if you fill out these trace, I might give you an extra point on your, on the homework that, extra few points, let's say, on your homework that has the lowest grade. So, so that's just an incentive for you to fill out the trace evaluation. So please send me your receipt after you fill out the trace evaluations. Okay, so that's it. I think this was very useful. And by the way, there are two reports. There are two presentations one presentation, which will be recorded, because we couldn't arrange for any of the participants to present today. So that will also be uploaded. Okay, any questions before we sign off?
Yeah, are you going to make a place on Canvas for us to submit the report, and should we each do it individually, or is it going to be like a team submission kind of thing?
Well, it's just like when you submit the homework. Do I have to make an assignment for you to upload?
Yes.
Okay, so I'll make an assignment for you to upload the report. Okay, I mean, yeah. So the other thing you could do is just to email it to me, but I think it's better to upload it on the so I'll make an assignment. Yeah. Okay, any other questions? Okay, so thanks very much. It was a nice term, and we go from here, and send me the slides and upload the report, and finish the trace evaluations. Great. Thanks, everyone.
Thanks, Professor.
Have a
Thank
good
you,
summer.
Professor.
Thank you, Professor.
Bye-bye.
Thank you.
Thank you, Professor.
Thank you, Professor.
Thank you.